This is Chapter 3 on complex adaptive systems. The previous chapter focused on the flows of energy and matter through ecosystems and on their structure. This chapter investigates the deeper logic in ecosystems and their component species, in how they work, how they come to be, and how they change. The plan is to look at dissipative structures, the maximum power principle, complex systems, complex adaptive systems, then tie it all together: ecosystems, complex adaptive systems, and gradients. Think about what happens when you put a pot of water on the stove and turn on the burner. The water at the bottom, next to the heated part of the pot, heats up. Since warmer water is less dense, it rises through the pot to the surface. As it rises, it's forcing the cooler, heavier water first to the side and then down toward the bottom. When the heated water reaches the top, it's exposed to the air. It transmits some of its heat to the air, which makes the water cooler. Meanwhile, the water that had been forced to the bottom has picked up some heat down there, so it starts to rise. Inside the pot, we get the pattern known as convection. If the heat source is in the center of the pot bottom, the heated water will rise to the surface of the pot, cool off, move toward the edge, then sink back down along the sides. There's a gradient between the heat of the burner and the relative cool of the air, and convection, by moving hot water up toward the air, speeds the process of reducing that gradient. In other words, convection is a dissipative structure. But it's not merely that it works to dissipate the gradient. It also requires that the gradient exist. When the right kind of gradient is there, it happens. When the gradient is gone, if you turn off the burner, it goes away. Structures like these aren't limited to stovetop settings. A hurricane is a massive dissipative structure. The gradient in this case is between the warmth of the ocean's surface waters and the cool of the atmosphere. The core of a hurricane is the eye, an area of low pressure that draws toward itself the signature swirling bands of heavy rain and wind. At the eye wall, the warmed air rises into the atmosphere, carrying the heat of the ocean up into the air. If you look where a hurricane has been, you can see its path, traced out in the zone of cooler water where the hurricane has done its work, moving heat from the ocean to the atmosphere. And where one hurricane trips over the trail of another, it loses strength. Moving over the cooler water, it doesn't have as much of a gradient to drive it. We can say that dissipative structures are physical structures that arise spontaneously in the presence of sufficiently large gradients. For example, convection or hurricanes. On the one hand, they can only come into existence in the presence of a sufficiently large gradient. On the other, they dissipate or reduce the gradient that fed them. Okay, fine. Hurricanes and convection act to dissipate gradients, but you might ask yourself why this happens. Why do we see dissipative structures pop up when there's a gradient at hand? The ecologist Howard Odum proposed what he said should be the fourth law of thermodynamics, the maximum power principle. This was the idea that during self-organization, system designs develop and prevail that maximize power intake, energy transformation, and those uses that reinforce production and efficiency. Why might this be true? For inanimate systems, the logic isn't obvious. Perhaps it's that a system that does a better job doesn't leave enough gradient to power any alternatives. For living systems, we'll have a clearer explanation later in the chapter. But before we get there, we have to take a detour, passing through complex systems and complex adaptive systems on our way to evolution. Start with an example of a complex system. Imagine a square grid stretching off potentially infinitely far in each direction. Choose any particular cell in this grid. It has 8 neighbors. And each cell has 2 possible states. It can either be on or off. There are 4 rules governing the changes in a cell's state from one period of time to the next. Whether you started as on or off, if 0 or 1 of your neighbors are on, you will be off. If 2 of your neighbors are on, you will stay what you were. An off cell stays off, and an on cell stays on. If 3 of your neighbors are on, you will be on, whether you started as off or as on. If more than 3 of your neighbors are on, you will be off, again, regardless of how you started. These are pretty mindless, mechanistic rules, yet when we set up a computer program to carry them out, strange things happen. Watch what happens to the two shapes in the small version of this grid. Watch it again. The shape on the left completes two 4-step cycles, each cycle taking it through a series of shapes until it ends up the same shape it started, except one square to the southeast. The shape on the right just blinks back and forth between being a vertical line and a horizontal line. These rules make up Conway's game of life, developed by a British mathematician in 1970. They're an example of cellular automata, systems where we don't set up rules for the system as a whole. We only set up rules for the autonomous parts of the system, in this case, the individual cells in the grid. Here, the rules don't say, make a shape that glides across the screen to the southeast, or make a shape that blinks back and forth between horizontal and vertical. All they do is tell each individual cell when to be on or off based on its environment. But the result is that certain shapes will flip back and forth in place, while other shapes will glide across the screen. The game of life is an example of a complex system. That's when a system as a whole displays behaviors or properties that aren't obvious from the properties of the individual components. In the game of life, the behavior is deterministically produced by the rules governing the individual cells. There is no randomness in how the thing evolves. If you know where you started from, you can apply the rules and figure out where you'll end up. And every time you start from one place, you'll get to the same state every single time. And yet the path and the end state aren't obvious from the rules.